Somebody please verbally confirm to me or by a text.
Is my voice audible? No. Hello.
Yes, sir. Yes, sir. Audible.
Oh, wait a minute. I think okay, just a minute. I think my speaker was on very low volume. Yes, please. Yeah, now can I get a confirmation?
Yeah, you are
Yes, sir.
audible.
Yes, sir.
Yes, sir.
Yeah, because see, this is a new machine, so the audio was not working in the morning, so I thought I'll just confirm.
Am I audible? Yeah.
Yes,
Okay.
absolutely audible.
Yes, sir. Yes.
Okay, Akshay, so we can start, I think.
Yeah. So Professor Pant, I mean, since my time he's teaching. I mean, before my time, when I was a graduate student there, he has been teaching. He has a very good experience in teaching. He is doing research all over the place. He's from aerodynamics, but he does lots of research work in uh, multidisciplinary optimization. And I have attended 2 lectures, 2 workshops with him, and he's an amazing teacher. And we are grateful to him for continuing to help us out in these workshops. So I'll hand it over to him for his next session. Thank you, Professor
Thank you
Pant.
so much. A very good evening to all the participants. We are coming at the fag end of the day, and I saw with the schedule that you have been exposed to various kinds of methods, starting from genetic algorithms, and then my colleague Professor Shimpi has also covered, I think PSO, ACO, etc., etc. So you have been exposed to various kinds of optimization techniques. Now, as you know, there are different techniques. Each of them has its own merits, its own demerits. There are a certain class of problems for which a particular method is suitable, and to the best of my knowledge, there is no method which is suitable for all kinds of. There is no one size fits all in optimization. That is the challenge as well as the frustration in optimization, because as a user who wants to optimize a function, you would be happy if there is one method that can just be taken by you and applied to solve your problem. But unfortunately, that is an ideal situation. So let us look at the situation in which this algorithm, simulated annealing, works very well. So friends, the scenario in which SA, as I will abbreviate it, uh, simulated annealing or SA, the scenario in which it is the most suitable and works very well is to look for the global optimization of multimodal objective functions. So when I say multimodal, I hope you appreciate that multimodal means there are many minima or maxima. There are many optima, and one or few of them are the global optima. That means the function value does not have a better value at any other point other than this one or these few points. And in this myriad of possible solutions in the landscape, we are groping in the dark literally and trying to find the global solution. So I will demonstrate to you a situation, if time permits, in which I'm going to run a code for you as a trial, and I'll try to show you a simple test function. And I'll try to show you, if time permits, how we can use it to find any one of the many global optima solutions. And then I will tune it so that there is only one global optimum, and we will see that wherever you start, it is going to hopefully converge to the same solution. So let me start by asking you a simple question. Um, in front of you is a one-dimensional function in which the function has design variable only one, which is x on the x-axis, and the fx is on the y-axis. And the blue line with all these a, b, c, d, etc. is the variation of this function. Now, if the function behavior is available to you, then there is no problem in locating the global minimum, which is f. Okay. So what I would do is that in this case, of course, I can visually acquire and say that there is no value lower than this. But now suppose I tell you that there is a black box called fx. You supply any value between the lower limit and the upper limit of x. And I want you to bet your life and guarantee that the strategy that you will follow is going to definitely give you F as the solution. So what strategy will you follow? So maybe can we just make it a bit interactive by asking some people to help out? What would you do to ensure that you always end up in F? The floor is open to any suggestion. Akshay, are you allowing people to unmute themselves and talk, or is there any restriction like that?
No, I mean, they can unmute themselves.
Okay, so then please, if you can unmute yourself, anyone can please unmute and share with me your view. I hope the problem is clear. Come on, guys, you have seen so many methods, you have seen so many things. This is not the first day of the seminar. This is the fourth day, I think.
Participants, please participate. Please,
Let's
please give your
participate. Now,
input.
your name is a participant, so you must participate.
It's like this is the third workshop, and it's really embarrassing for us. We are inviting, I mean,
No, no, it's not embarrassing. This is unfortunately, we have a culture in our country where asking questions is not considered good, whereas we want to encourage asking questions, and that sets, into the psyche of the individuals, unfortunately. So, out of respect or out of fear, whatever, they don't ask questions. But unless you ask, you will not get the understanding. I can keep on talking for 2, 3 hours. I am a professor, I'm used to talking, but you will not be able to really appreciate, and it will be very boring.
and I mean,
So come on, guys, anyone.
quite a few of us are already professors in other colleges. So it's not that you don't understand what we are saying.
Oh yeah, I'm sure they must be teaching all this.
Yeah.
I'm quite sure that they'll be teaching all this. But then, can someone hazard? And there is no there's no negative marking. Nobody will be thrown out. So I'll just wait for some time till anyone. And if nobody, then I think Akshay, you have to give the answer.
Yeah, sure. I missed a part of it. So how to reach F
So,
starting from any X?
but remember, your life depends on it. You cannot say, I'll try this and then maybe. Nine. There is a function, single variable function. There is a black box. You give X, it gives you Fx. There is a lower limit, upper limit. If you have to give a strategy, and if your answer is wrong, you will be short. That is the kind of stakes. So you have to be very, very sure of the strategy.
So
I want to find the F. I want to go to F.
So what I can do is I can choose X. So I'll do a random number generator.
No, actually, sorry, you don't have to choose X. You can even tell me this is the strategy I will follow. You can calculate the function multiple times. No problem.
Yes. So what I'll do is I'll put a so I'll use a random number generator at a particular X. I will limit that delta X by some value, and I'll ask the random number generator to generate that number, and I'll move around, and I'm sure at some point in X I'll see the minimum.
But how will you be sure? For example, if you start somewhere near the point B, okay, you start somewhere near point B, let's say on the left of point B, and you put delta X on right and left of B, you will think that B is the minimum.
Yeah.
But you will be shot dead because there is a point D also which is better than B. And of course, there is an F, which is what
So I'll not stop at B. I'll not stop at the first minima I'll reach. I'll keep on iterating till I reach 3-4 minimas, and I'll keep storing them, and then whatever is the best minima, then I'll choose. So if I wait long enough, I'll reach F.
Okay. This is also acceptable, but then this is nothing other than just searching the whole domain blindly. Then where is the optimization? I could also say that let me divide the domain from X minimum to X minimum into 1 lakh equally spaced points called as a grid search. And now I calculate X at all of them, and then I pick up the best of them.
No, but then I'm choosing random numbers, so maybe randomly I'll hit minimums what I may not have to.
But you will not know, na?
Yeah.
You will not know. See, using random number for this particular approach doesn't give you any advantage.
Yeah.
Because what you are doing is essentially hit and trial. So when you do hit and trial, using a random location doesn't help you, because you should have some better way of sorting it out. Okay, let's see if anybody else can suggest a strategy. So let me suggest you one strategy. One strategy could be that I divide this domain into 10 equal parts. 10 is just a number. 10 equal parts. And I now start a local search from each of the randomly started random or edges of each of these 10 points. And then I store these 10 minima values. Maybe, if I divide the domain exactly into 10 parts and all domain is covered, the best of those 10 optimum is the solution. Because as long as you are able to trap the minimum solution in a domain where it is monotonically decreasing or increasing, you can never be sure. So for example, if you look at any greedy algorithm, okay, and there are many algorithms which are very greedy, they will simply get stuck in the nearest local minimum. So if you start from A, it will end up at B. If you start from C, it will end up at D. If you start from E, it will probably go to D again, because you are on the left cusp of the solution. So it will go to D. It won't go on the right side because it is increasing. And if you start from G, it will go to H, but we want to go to F. So the only way that people suggest is multiple starts from various initial X values, which could be random, which could be structured. But that is a problem. Now let's look at the world of non-greedy algorithms. So what is the greed here? Why do we call them greedy? Why do I say that if I use a greedy algorithm, it will go to the nearest local minimum? There must be a reason. So what is the meaning of greed here in optimization?
So always going towards the best possible solution is the greed.
Yes. So not accepting any solution which is worse than the one obtained so far or one obtained previously. So if you are doing a minimization, you will not accept any point where the function value is more than the current value. That is why from E we can never go to F, because E is just on the left of the peak. So when you go on the right from E, the algorithm will say, no, this is not a good direction. This is not a descent direction. This is an ascent direction, and we are minimizing. So it will say, no, go towards this side. Towards this side, it will keep on decreasing. It will stop at D. Beyond D, it will not go up. Okay. So greedy basically means, now non-greedy means that when you are minimizing, you should permit occasional uphill moves. That means I want to go to the bottom of the domain, but once in a while I should be allowed to go uphill. Remember, it is occasional, and this occasional is a very loaded word. We have to define this occasional and ensure it. So it should be done sparingly and in a controlled manner. It's not random. It's not just random. It's not arbitrary. It has to be in a controlled manner. So what we do is, if you want to go to the global minimum, you should go to the large, you should be allowed to do large uphill move in the initial stages. That means in the initial stages, we will be very liberal. Any amount of worsening in the solution will be accepted because the point will move in the domain. So you will do a good domain exploration. But as you, okay, and the purpose of this is better domain exploration to avoid getting stuck in the local optima, and remember, only once in a while. Otherwise it becomes a random search. Then you are no better than random search. Now, one of the methods about which I'll talk today, there are many nature inspired methods. One of them is inspired from metallurgy, and that is the process of annealing. So friends, all of you must have, like me, must have studied this annealing in your undergraduate courses in materials, because annealing is a very important process in manufacturing. Okay. So, is there anybody in the class or in the group who can tell very briefly what exactly is annealing and what is the purpose? What do we do when we anneal a material and how do we do it? Anyone? In the meantime, I'll just go and switch a fan so that I can be a bit more comfortable. Yeah, friends, please define annealing or explain annealing.
It helps the any complex parts to work.
Very right, madam. Once you do working on a component, okay, it helps. So definitely, whenever we do any manufacturing activity on a material, maybe cutting, maybe grinding, maybe any other activity, forming, machining, we normally do annealing after that. Correct, very right. But why do we do annealing? What is the benefit of annealing?
Refine the microstructure, I guess.
Exactly. So why do you refine the microstructure? What is the purpose? What you say is right. But why do we want to refine the microstructure? So let me give you an idea. When you do a lot of working on a material, you actually build up internal stresses. And annealing is done to relieve these stresses. Okay, annealing is done to relieve the stresses. And there can be a lot of hardening of the material because of working, cold working. So annealing is like softening. So you don't want internal stresses. So what I'll do is I'll take you through a small class on annealing. Okay. And I remember my professor from my college who taught me annealing today, with all due respect and regards to him. It's a type of heat treatment that causes changes in strength and hardness of a material. The process of annealing is very straightforward. You first heat a material to be annealed above a critical temperature. And although I have mentioned melting point here, but in reality, you will go not at melting point, but very much near the melting point. Okay. So you heat the material to very large temperature, almost near its melting point. And then after that, you maintain at that temperature for a reasonable time. So you maintain a suitable temperature at a reasonable time. And then after that, you allow it to cool slowly. So there are three important steps, and these three steps will be also explained to you when we look at simulated annealing. Because simulated annealing is nothing but simulating the process of annealing in optimization, and there is a one-to-one coherence between a step in annealing and a step in simulated annealing. So three things: enough temperature to be given, keeping enough time to be given to be at that temperature, and cooling, but cooling slowly. What is the purpose? To induce ductility and soften the material and to relieve internal stresses, as I mentioned to you. Okay. So what are the features of annealing? So the structural properties that ultimately develop in the material, they are a function of how slowly you cool, how patient you are. If you give annealing sufficient time, that means cool slowly, you will get a better softness. If you do what is called as quenching, that means sudden cooling, then you are going to get very good hardened surface, but it will be brittle internally, and then it cannot probably take loads. So if the liquid is cooled slowly, what happens? What happens is that when I say liquid, basically it is molten state now. That's why it is called liquid. You have a metal, but you have heated it so much that it is almost in the molten stage. So you call it like a liquid. So what happens is if you give enough heat to the material, then you are giving freedom for the atoms to literally recombine with each other into various positions. We call it as moving freely. And in the process, the internal stresses are relieved and large crystals are formed. Large crystals are the ones that actually have lower internal energy, and therefore they have better soft characteristics. But if you cool it very quickly by dipping in water, Okay, then the crystals will contain imperfection and the material becomes hard but brittle. In some applications, you may require surface hardness, but brittlity is not a good feature for standard components. Now, annealing is done by basic physics. Okay, so what you do is you provide a lot of energy because of high temperature. This particular energy allows the various atoms to explore crystalline states. Each state corresponds to certain internal energy U, and if you give enough soaking time, then various states are explored randomly and it slowly converges to a state that minimizes internal energy provided you cool it slowly. This is annealing. Now, in 1953, when computers were still very new and the maniac computer of the Los Alamos laboratory was almost like in a Hoj building. During that time, these four authors, Metropolis, Rosenblatt and Teller, what they did is they gave a mathematical model of the annealing process. Okay, so these guys are the inventors of the Monte Carlo method, which is also another method where you can have random positions for a particular state. They were invented this method, and this method is basically a statistical approach to solve a n-body problem in a deterministic fashion. So they were the first to give a mathematical modeling of the annealing process. And recently I did a search and I found that there were more than 46,800 citations for this paper. Remember, it's a classical paper of 1953. Now, fast forward to 1983, you have a paper which is learning from the original paper by Metropolis et al., applying it to optimization, and it gets more citations than the original paper. Why? Because this paper appears in the Science magazine, and also this paper actually makes the simulation that was done or the modeling that was done for the annealing process. They found a very deep and useful connection between that and multivariate or combinatorial optimization. As all of you might be aware, the term multivariate optimization is used for problems where there are more than one variables, x1, x2, x3, x4 up to xn. And combinatorial basically means that these design variables, they only have fixed integral values. Okay, they don't have real, you cannot say 3.2 or 3.9. It's only 3 or 4 or 5. They have integral values. Okay, and a combination of these integers, okay, combination of these integers is a solution. Now, it need not be only integers. It could be possibilities. It could be like on a chip, you have locations for transistors. Okay. So, because if I am going to use only numbers, whole numbers, one can also call it as integer programming. But this is different from integer programming. Here, there are only a particular possible values available. I would say that integer programming is a subset of combinatorial optimization. So these guys, they actually studied. So imagine someone wrote something in 53, in 1983, these people come up with the connection. Similarly, not very far away, just a couple of years later, another gentleman called Cierney, he also came up with the same kind of understanding that a Monte Carlo algorithm can be used to find the solution to a classical problem called as a TSP, a traveling salesman problem, which, as many of you might know, is a problem in which there is a salesman who has to cover n cities once each time, and we have to find the route to be taken for minimum cost. And there can be many ways of defining the cost. There could be penalties for crossing a particular river, etc., etc. Those are complicated versions of TSP, but a simple TSP is that you go A, B, C, D, E, F, G up to Z or whatever, and you have to do it only once, and the minimum distance is the solution. So this guy, Cierney, was trying to solve that problem, and he discovered that one could solve it using the same thing. The difference is that he got only 4,720 citations because his journal was a very specific journal on optimization theory and applications. And also, this is not so very widely reported journal as compared to Science. So this is the background and the history. Okay. So it's a numerical simulation of the annealing process and little bit of mathematics to numerically explain how a particular state in the material is either accepted or rejected. There is a Metropolis-Hastings criteria, which stands for if there is a particular combination or a crystal state during the annealing process, which has a total energy capital E, then the probability of that particular state to be accepted is P bracket E, and that is equal to the exponential value of, that means E power minus capital E upon KT, where capital E is the energy, small k is the Boltzmann constant, which is a very, very small number, 10 power minus 23, and T is the temperature. So now by looking at this particular equation, you can easily find out that if the relative value of capital E, because K is a constant, though a very small number, it's a constant. If the relative value of E and T are almost similar, that means when temperature is very high, or when the value of capital T is almost like the value of capital E, or much more than that, then the probability value will be very high. On the other hand, when the temperature value T is small, then for the probability to be high, E has to be also very small. In other words, when temperature is high, the probability of acceptance of a particular state, even though the energy level is high, is very high. When the temperature is low, the probability of an state to be existing even when the energy is reasonable is low. But if T is very small, then for selection of a particular state, E must also be very small. We can look at some other way. We can consider capital E as the energy as something that is to be minimized. We would like to have a state where the energy is minimum because that corresponds to the least internal stresses. And to do that, we are kind of randomly going in the domain and looking at various possible combinations. So when the value of T or temperature is high, we are very liberal. Even when the value of E is reasonably high, we are going to accept it. But as we go in the algorithm, we keep on gradually reducing the value of capital T or the temperature using a control parameter, which I will talk about. So towards the end of the exercise, or as the solution converges, you will find that the probability of acceptance of bad points is going to be lower in proportion to how bad they are compared to temperature. Because E represents badness of a solution. Because we want to minimize E, best E will be 0. So our aim is, in the beginning, give very high temperature, be liberal, explore the whole domain, look at various combinations. Slowly, as the algorithm proceeds, reduce the value of T. It could be linear, it could be logarithmic, etc. There are many ways of doing it. But towards the end of the algorithm, there is a non-zero probability of a bad point to be accepted, but the value is very low. So now let us look at 1:1 correspondence between the thermodynamic simulation and the optimization. So the system states in the thermodynamic simulation corresponds to possible feasible solutions of the optimization problem. So one candidate optimized solution, like a combination of x1, x2, x3, it's a possible solution. That is the system state. The cost which is minimized in the optimization is equivalent to the energy E that I mentioned to you. the neighboring solution would be corresponding to a change of state or moving in the domain to get the new point. Temperature of a mathematical simulation is a control parameter here, and a heuristic solution which converges to some solution is a frozen state or a quenched solution. Now, before I go ahead, it is very important to understand that all of you have appreciated what exactly is the metropolis testing criteria, because this is the crux of simulated annealing. So if you have any doubts, I think it's a good time for us to spend a couple of minutes to sort those doubts. So anyone in the audience, do you have any query or any clarification regarding the metropolis testing criteria? So either all of you are masters in simulated annealing, so you know this and you are maybe laughing at me saying, what is he talking about? Or you are not, forthcoming and asking me questions. I don't know. I assume the first one is true. But I hope everything is clear. Akshay, what do you think? Is it clear to you?
Well, I mean, I can say that by fixing the energy, we are trying to fix the amount of travel that we will have. I mean, that is in a sense what is related to simulated annealing when we are heating it.
No. Sorry. That is a problem. See, we don't have any control on energy. Energy is corresponding to a particular system state or a solution. Okay, so when I am at a trial point, let's say that point is x1 or whatever name you call it. I go to another trial point. I don't have any control. So I cannot proactively find a point where energy is minimum, because if I could do that, it's like saying that the landscape is in front of me. I just pick up the point with the minimum energy. No, I don't know. So what is the energy of a particular state is not known a priori. But what you do is you are at some point. That point basically means a particular combination of the variables, design variables. It corresponds to some objective function value. Then you say, okay, let me try a new point. I'll tell you how we go to a new point. That's a different matter. I go to that point. That point has got some other objective function value, which is analogous to the temperature. The energy. Now, if I know proactively that this energy is, so let me ask you a question. Let's say you are minimizing a function, and you are at a trial point number 1. I'll call it as TP1. At TP1, the function value is 100 and you are minimizing.
Okay.
You go to point TP2 randomly and the function value is 50. What would you do? Would you accept it or would you not accept it?
I would iterate a little bit more.
Why are you so worried? If a solution that you have got is better than the previous one, grab it. Now, what is the problem?
Yes, I mean, I will grab it, but I'll move forward. Yes, I'll grab it.
Yeah, you will see. We have to keep on moving till we meet the stopping criteria.
Yeah.
So from a point where the value is 100, you go to a point randomly where it is 50. Oh, you are lucky. You will say, great, thank God, I will grab it. So I will say, forget the previous point. This is a better point, and maybe I'll keep it in my memory if I don't have a problem with storing. Now you go to another random point. The value there is 62. Now what do you do?
So then again, like based on my criteria, I may accept it or I may reject it.
So how do you decide?
So again, like we were talking about the greedy algorithm or non-greedy algorithm. So if I'm not greedy, I may accept it based on some random number, or I'll accept it.
No, not on some random number. That is random. No, that is purely random. I'll tell you what we do.
Okay.
If the point that you get is worse than the previous point, you will say, if I'm greedy, I'll say I don't want to accept it. Correct? You will come back to the previous point where it is 50. But in a non-greedy algorithm like this, you will say, hang on, this is 62. It was 50 earlier. What is the difference? The difference is 12.
Mhm.
How good or how bad is the difference of 12 in the current scenario? What is my temperature right now? It's very high. So what you will do, you will say, okay, let's say for example, temperature is 20,000.
Mhm.
So you will say, okay, e power minus 20, okay, e power minus 12 upon k into t.
Okay.
So you will say the probability will be some number.
Mhm.
If the value of t is 20,000 and e is only 12, then there is no problem at all. You will get a high probability of selection because your temperature is much higher than E.
Yeah.
But if this decision is taken after few hours of walking, when T itself is 20, then 12 and 20 is near each other. So there what will happen is for the same delta E, you will not get a higher probability of selection. So what you do is you accept a good point, but don't reject a bad point immediately. Give it a chance to go through this criteria, and this criteria will be slowly tightened. Okay. So by being liberal in the beginning, you are allowing the domain to be explored, but hopefully you will be near the optimum solution. And then when you want to converge, you don't want to arbitrarily move. I'll explain to you by an example also. Now, friends, the algorithm is very simple. It can fit into one slide. That is the beauty. There are three things which are to be decided to start. The first is, what is my solution space X? That means what are my design variables X1, X2, X3, etc. Second thing is, what is my objective function F? And am I minimizing or maximizing? Unfortunately, the basic assay algorithm can only minimize, just like you must have been told that genetic algorithms can only maximize. It can maximize the fitness. Now, if you want to use GA for minimization, you have to tweak the fitness function in such a way that the lower value of F gives you higher value of fitness. Similarly, you have to do some little bit of manipulation here. If you want to maximize using SA, then you have to tweak the objective function in such a way that the lower value of F corresponds to higher value of your objective function. And the next thing you have to decide is neighborhood structure. That means I am at some arbitrary trial point in the domain. The domain is quite large. Let us assume that I am looking at a two variable problem and my screen is a domain. So the bottom left is the origin. The right hand side of my screen, let us say it is 10 inches and the vertical is 6 inches. So the domain is 0, 0, 12, 0, 12, 6 and 0, 6. Correct? So one can say that I am going to explore the entire domain, or one can say no, I will be exploring only a small part of this domain. That is called as the neighborhood structure. Now, my question to you is, okay, I'll come to the questions later. So these three things have to be decided. Okay, clear? Now we go to the next thing. You have to now select an initial point S0. You have to select initial temperature T0, which only requires to be more than 0. And you have to select a temperature reduction function or a factor called alpha, which will be used to reduce the temperature after some iterations. Okay, so I'll give you some suggestion. S0 is determined randomly. Okay, randomly you can calculate, you can give a trial point S0. Temperature T0, it has to be sufficiently large. In an annealing exercise, it has to be near the melting point. But here we hit the first problem. We don't know what is the melting point because we don't know the function behavior yet. So this is something that needs to be tuned, and I'll explain to you how. The next thing is the temperature reduction function. At what rate will I reduce this temperature as the iterations proceed? Do I do it like 50% each time, or 80% each time, or 90% each time, or 5% or 10% or logarithmic or whatever? There are many ways of doing it. But this is to be decided. Okay, now what you do, once you decide these 6 things, now you do two iterations. The first one says that repeat till some stage. Let's look at the inner one, the green iteration loop. What you do is you randomly select some value of S, which is in the neighborhood of S0. And the neighborhood is decided by you, by the way, right? In the beginning, you have decided the neighborhood. Now you are at S0, you know the value of F0, the objective function value. Now you calculate F at S, the trial point, and then calculate delta F, which is equal to Fs minus Fs0. Okay. Now, since you are minimizing, you would definitely accept a solution where the value of Fs is less than Fs0. That means if delta F is less than 0, you should be happy and you should say, forget S0, the new S is my S0. Otherwise, in a greedy algorithm, you would say, don't accept the point, but here we say, no, wait. Generate a number R, which is between 0 and 1, randomly determined. Let's say it is 0.3. Now, calculate the value of e power minus delta f by t. Now we have knocked off the value of k here. We have forgotten the constant because k is a constant. You could consider this t as a Boltzmann constant into a temperature. So we forget about that. So now you see what we are doing. We are saying e power minus delta f by t. So if delta f and t are very near each other, then what will happen is e power minus delta f by t will be a number that will be very small. And r is a number between 0 and 1. And maybe this e power minus delta f by t will be 0.01. So now between 0 and 1, the number 0.01 is very much near 0. So the chance that, or I should say the other way around, sorry. So if the value of, so the value that you pick up between 0 to 1, which is let's say 0.6 or whatever, if that number is less than this particular ratio, that means the value of e power minus delta f by t is say 0.02, and the number that you get from 0 to 1 is 0.01. Only in that case you accept, otherwise don't accept. So in other words, when the value of capital T is very, very large as compared to delta f, then what will happen is this e power minus delta f by t will become something like 0.89, 0.90, 0.95, such large numbers. Okay. Now, if your number R is less than that, I mean, you have to accept it. Got it? So this is how they proceed. Now, this is, you keep on repeating this until you reach some number called as maximum iteration. Remember, we have to soak at a temperature for a given time. So here temperature was T0. We need to do it. So this iteration number will be, you have to do it many times. And then you say, okay, enough. Now I reduce temperature T to alpha times original T. And then I repeat. And I keep on doing this iteration till I meet the stopping criteria. And when that is done, I say that S0, which is now my current memory for the best point, that is an approximation to the global minimum solution. This is how it runs. Okay. Now, are there any queries regarding this particular algorithm? So for example, I'll give you an example. Yeah,
we can still miss the global minimum, right? It will
yes,
again.
But I'll tell you, I can confirm. No, see, the thing is, you are looking at it very myopically that we will miss it in one iteration. But see, this happens in multiple iterations. Okay. So the chances that you will miss the global solution depend on how bad is the choice of the various parameters. I mean, you can always make an algorithm fail. Okay, one way to do it is be impatient and quench the solution. Yes, it will not cool. It will not lead to reduction in the. So if you are impatient, so what you do, you choose T as very low value. You want T to be more than 0. I'll say, okay, I'll take T as 20. Instead of 20,000 or 2 million or 20 million, I'll take it just as 20. So what is happening is, if your function value delta F is near about 20, then it will be very, very harsh and it will not accept. Whereas if you take the value T0 as 2 million, in the beginning, almost everything will be accepted. And slowly, as T reduces, and it comes to a particular value, then you will find the function, then you find that the metropolis criteria is tightened. So mathematically, it can be proven that this algorithm is going to always converge to the global optimum. But there is a catch. The catch is that to ensure that mathematically, you have to give it infinite time. That means this parameter alpha should be 0.9999999, something like that. So the temperature is very, very slowly reduced, and also the value of T0 is very, very high. So you make T0 as positive infinity and you make alpha as 0.99999. It will take your lifetime to slowly solve, and then there is a guarantee that it will give you global optimum. But we don't have so much of patience and so much of time. So therefore what we do is we accept little bit of non-optimal solution. But what will happen is, if the minimum solution is 2.0011, it will stop at 2.00, and then you will say no, fifth decimal place is not matching. But that is practically of no big difference to you, isn't it? So for all practical purposes, you will get the global solution. But if you go for mathematical rigor, then we'll say, okay, then guy, please give infinite time and infinite function evaluations, and I'm sure it will go to global minimum. There is a proof for this available. I will talk about it a little bit later. Any other query about the algorithm? Because if you understand this and the philosophy behind it, you have got the meaning of SA.
So it seems
so maybe
participants don't have
sorry.
any questions. Participants don't have any questions, it seems. Yeah.
Okay, we'll go ahead, no problem. Features of SA. First of all, nowhere in the previous slide you heard the term derivatives or Hessians. And nowhere you heard that you should always go for function improvement or descent direction. You will have to agree with me that it's a very simple architecture. Convergence to global optimum guaranteed, but requires infinite function evaluations. And the mathematical proof of this has been given by Larhofen et al., Larhofen and Arts, in this particular textbook. They use something like a Markov chain theory to show that the infinite Markov chain of an optimization algorithm in SA converges to global minimum solution. This kind of a proof is not available for genetic algorithms, but it is available for simulated annealing. Now, we have some parameters. As you saw, there were parameters there. So solution space X and objective function X. This can be defined only by the user, right? I don't know what your problem is and what your objective function is. You must decide. Neighborhood structure. How much should we move in the domain when we are exploring near the current point? This has to be done adaptively, and I will show you how it is done. Initial point S0, no problem. It can be selected randomly. Initial temperature T0 and temperature reduction factor alpha. This has to be chosen very, very carefully because it ensures proper annealing or it makes it quenching. And then you have stopping criteria. One simple method is maximum number of function evaluations, or you can say minimum improvement in F acceptable over so many iterations. So let me just correct this. I forgot in last k iterations. So you can say that, okay, I will wait for 3 iterations or 4 iterations. And in my previous 4 iterations, if I do not get improvement more than so much, then I'm saying that, okay, no point in looking at decimals now. We can stop. Okay. Now let me give you a small demo of working of simulated annealing. So what you will see is the vertical red line that you see corresponds to the trial point S0 and then subsequently all the points which are investigated. This is a one-dimensional function which is a hill climbing exercise. So what we want is we want this red line to stop at the peak value. Sorry, Hemant Kumar, I am not able to hear you.
Hemant Kumar is muted.
Achha, sorry. I thought there was some sound from him. I may be wrong. So we want the vertical line to stop at the place where the peak is there. And we are starting with a temperature of 25. This has been chosen very carefully after looking at the function, but don't think that this temperature you should take. This is actually a very low value. And I'm going to click on this file, and what you will see this red line moving in the entire domain. Ideally speaking, in the initial stages when temperature is high, 25 is high in this case, the red line should be oscillating all over the domain for better domain exploration. But as temperature reduces, the red line should oscillate only near the global minimum, which is at this place. And at the end, it should stop below this. Okay, so let me try. So this is running again. Of course, it's the same diff file, so it will just keep repeating. We are not starting from a new random point. This is just an animation of one particular case. So did you observe what I told you? That in the beginning, it is oscillating all over the domain. When temperature is low, it can still oscillate somewhere outside, but when it is very small, it's not going outside this place. So this is a small demo of the working of this algorithm. Okay. Now, what is wrong and what is right about this algorithm compared to the other methods which you have studied, and also with respect to the conventional methods? I would recommend that you do not venture near this algorithm if your function evaluation is time consuming, because the number of function evaluations in SA are going to be at least 1,000 times more than those in the classical methods. Okay. And also the exact optimum solution will not be reached in finite time. It will require a lot of time. Suppose you are maximizing fx equal to x square. Okay. Then it would be a stupid thing to use SA for optimization, although it will work and give the solution to you. But there are better methods available for optimizing such functions. Because you know fx equal to x square, the function is known to you. You know it's a quadratic. So I would use a Newton-Raphson method and get the solution in 2 iterations. But if it is a black box, and if you know beforehand that there are multiple solutions and one of them is the global optimum, and I want to get that one, then you should use a method like this, provided the function evaluation is not a constraint for you. Second thing is the neighborhood, neighborhood is, there is a hint available, but what temperature to take, what is the temperature reduction parameter, and other parameters which are required, how much time to give for oscillating in that domain. That is called as tuning. And this tuning of parameters is a very time consuming process. It comes by experience and by trial and error. And sometimes I have found that in a complex problem, if you solve the problem in 10 days, you may spend 5 days in just tuning your parameters. But once you tune the parameters, for that class of problems, it will work like wonder. Another constraint, another problem of this method is that you cannot specify constraints directly. Like in Lagrange multiplier, you can put constraints, or in other methods, you can specify constraints directly. You need to use a penalty function approach. That means you have to artificially penalize constraint violation. Okay. So these are the problems. Inability to handle constraints directly. Constraints have to be added as a penalty function. Tuning requires a lot of time and patience. And function evaluations are abysmally high, too high. So therefore, you have to be careful when you use this method. I'll give you an example of a penalty function, very simple penalty function, an additive penalty function. We say that the objective function is equal to the calculated objective function plus summation of penalty coming from each of the k constraints. And what is pk? Pk is basically one multiplying parameter called as ivk. This parameter will be 0. Will be if the value of the constraint is more than the tolerance. For example, sometimes you have a constraint saying that the value of this equation should be 20 plus minus 2. That means you are allowed from 18 to 22. So the tolerance will be 4. So IV will be, it is equal to 1 if the constraint is more than tolerance. Otherwise, that means it is met. So therefore it will be 0. IACTK is something which is used by you just to define whether a constraint is active or not, because sometimes you want to run the algorithm with 10 constraints active, sometimes with only 8 of them active. So now instead of changing the code, you just in your data file change IACTK as 0 for a inactive constraint, and then it will not bother about the penalty for that. Weight, WK is a weight. That means how much should be weighted, how much is the violation. Violation of constraint 1 versus constraint 2, which is more critical, how much? Is it 10 times more critical or once more critical? That number. This also is something which is very subjective and you have to give it. And CONSTRK is the value of the constraint, the numerical value of the constraint. So this way you add a constraint, you add a penalty for each constraint violation if it is violated, and if you bother about its violation with a proper weight added to it. Okay. Now, where is SA used? It is used in essentially in combinatorial problems. That is how it started. So VLSI and computer system design, there was a problem solved where more than a lakh transistor, more than 10 lakh transistors, a million transistors are there to be put on the chip. What should be the location so that the path for the current is minimized? Similarly, there is a network of computers which can be put at various places. What should be the optimal location so that the network delay is minimized? It has been used for sequencing and production. I remember one of the first project I did as a consultant when I joined IIT Bombay many years ago. Just when I was fresh, I took up a problem on optimization of the there is a bearing company near our institute. They wanted to optimize the usage of their furnaces. They had 2 furnaces and they had 5 types of bearings. So which bearing, how much in which furnace should be put so that we minimize the total downtime. So I could solve the problem with my colleague from computer science using simulated annealing. Similarly, transportation scheduling and timetabling, it's very popularly used all over the world. Then some mathematicians realized the potential of GSA for the combinatorial problems, and they gave us a solution or an approach to address continuous and mixed functions also. So if you implement that particular scheme, and I will show you that if my time permits today, it can be used for engineering design, it can be used for statistical function, banking, share market analysis, etc. So multiple usage. Okay. Now, we have seen the application of SA for a combinatorial problem. Now I want to talk to you about how it is utilized for continuous variables or mixed programs. For that, we have to thank 4 mathematicians, Corana, Marchesi, Martini, and Ridella. They have given in ACM transactions a paper on minimizing multimodal functions of continuous variables using SA. So they have given an iterative random search procedure with adaptive step size reduction. That is their huge contribution. Remember, the neighborhood has to be adaptively modified. The reason is as follows. If you are going to explore the entire domain every time, this is very much like a random walk. You are just going randomly in the whole domain. But if you become greedy and look and you search the domain only in the neighborhood, then you are being very greedy and very harsh. So you will miss the optimum points, which is what I think Akshay was saying in the beginning. But if I constantly control the neighborhood so that I am very liberal in the beginning, but as I proceed further, I reduce the neighborhood structure, then there is a good chance that you will be oscillating near the global solution in the end. But they have given a very interesting criteria. They say that in every iteration, certain moves are accepted and certain moves are rejected. Why is the particular move accepted? Because it results, there are two reasons. No, sorry, there's only one reason. A particular move is accepted either because it is giving you a lower objective function value than the previous point, or because you went to Metropolis Hastings criteria and they said that please accept it. And when is a particular move rejected? When the objective function value is more than the previous one, that means it's a worse solution, and Metropolis criteria says rejected. Only then you reject it. So they say that if you maintain a 50-50 ratio, almost 50-50 ratio between the two, you are doing a good job. Neither you are too liberal nor you are too harsh. Okay. Then they tested this against various test functions and also other existing algorithms like Neldemead simplex, adapted random search. They use it on some test functions like 2-dimensional and 4-dimensional Rosenberg function. They found that the SA algorithm always reached global minimum, but it needed 500 to 1000 times more function evaluations compared to the simplex. Then they applied it to parabolic multiminima, discontinuous functions, 20% lower total evaluations compared to other methods where you have to do multiple starts. There are two things still pending. How do we decide initial temperature and stopping criteria and assay parameters? So let me show you this, but let me talk to you about this particular code. So now the algorithm given by Corana et al. Was implemented by a gentleman called Bill Goff. Bill Goff is an econometrist and he published this paper in Journal of Econometrics based on the algorithm that I discussed before. And he also provided the Fortran program of this particular code on the internet. And it is such a strong method that it is a part of a commercial optimization package. Very well tested for many econometric problems. It was tested for 4 econometric problems and 3 optimization problems, and it was found that it is the best amongst all. And what are the improvements? Goffe has given not only the algorithm, they has also solved the problems. One is, how do you test for the globalness of the solution? How do you decide the iterative step size adjustment? And how do you tune the parameters? He has given a detailed explanation in his comment files in the algorithm, which code which is easily available. This is the full algorithm. I'm just going to go through this one by one. Okay. Akshay, how much time do we have? It's 7:20.
I mean, since we started 15 minutes early, so we have, we have time. So half an hour at
Because
least.
I want to keep half an hour for the trial because the audience will appreciate the algorithm only when they test it and when they try to make it fail. Okay. It's a challenge I want to give them.
So we have
So I'll
gone up
finish
to
this in the next 5 minutes.
we have
Yeah,
gone
yeah,
up to
we'll go up to
8:30 in the
8.
past. We have gone up
No,
to
I don't
8:30 in
think
the past.
No, we will go beyond 8 only if the audience wants, otherwise we'll stop. Okay. So let me
Okay.
finish this. So first you do is you initialize all the parameters. Okay. All the parameters which are required, you initialize them. I'll tell you what the parameters are. Now, what you do first is you perform a cycle of random moves, each along one coordinate direction. That means if you have a function with, let's say, x1, x2, x3, three design variables, what you do is you select a random combination of x1, x2, x3. That is over the trial point. You calculate the value of f. Now what you do is you keep x2 and x3 same and just change x1 in a small neighborhood. Okay, that is called as each along one coordinate direction. So what you do, you change x1 to some x1 dash, x2 is same, x3 is same. Calculate the objective function f, accept or reject each point according to the metropolis criterion. If you get a solution which is better, accept it. If you get a worse solution, don't reject, ask metropolis and accept or reject. And after you do this, you repeat it for keeping. Now what you do is, now you change only x2 in a small neighborhood again, and then you change x3 in the small neighborhood. So by this stage, when you do this particular stage, in case the number of design variables n is equal to 3, can you tell me how many function evaluations would have been done by this time? How many function evaluations would have been done if I do one evaluation in the beginning for the randomly determined trial point, that is 1, plus for each of the n design variables, I do a one-dimensional move. So when I reach this particular box end, when I reach somewhere here, how many function evaluations would have been done? What do you think?
Really infinite, sir.
Why infinite? You are performing a cycle of random moves each along one coordinate direction. Accept or reject each point according to the criteria and record the optimum point so far. So if I have three variables x1, x2, x3, I will start with x1 0, x2 0, x3 0, the initial trial point. I will do one evaluation. Then I will change x1 0 to x1 1, but I will keep x2 0, x3 0. I will do one calculation. Then I will change only x2, keeping the x1 and x3 the same. And then I will do it for x3. So how many will it be?
So the number of variables plus 1.
Exactly. So it will be 1 plus n. Very right. Thank you so much. It will be 1 plus n. But remember that when we do 1 plus n evaluation, so let us forget about this 1. The 1 is the initial point. I'm not going to count it, let us say. Okay. So I have done n function evaluations. Now, any of these 3 points which I have, or n points which I have calculated so far could be the current S0 value, because you are saying record the optimum point reached so far. So one of these 3 will be my point when I come to this one. Now you ask a first question. Is number of cycles ns, which is already initialized in the initialization box, have we reached that? No, then go back. Okay. So this is the first one. Na? So ns is equal to 1. You come here, you say number of cycles is more than, no, this is just 1. Go up. Again repeat. Suppose ns is equal to 10. Then how many function evaluations will be done when I come to this yes?
Around 12.
Huh?
12.
Why 1? It will be, why 1? I have to do this ns times, no? I have to do the rectangular box ns number of times.
It's multiplied by variable number plus 1.
So forget that plus 1 for the moment. So it will be n into ns. Do you agree?
Yes,
See,
sir.
I am saying that this internal box, do it ns times. And in the internal box, I do 3 function or n function evaluations. So therefore, when I do this, I come to yes only when I do it n into ns function evaluations. Am I right? Come on, guys. Are you not able to understand? Then tell me. I'll repeat it.
Yes, yes. So it's ns times n. Yes.
In the rectangular box, I have to do n function evaluations where n is number of design variables. And I have to repeat this cycle ns number of times. So therefore, the functions till this point will be n into ns.
Into ns, yes.
Now what I say, okay, enough. I have done n into ns functions. Now I should look at what has happened in these n into ns functions. And I should adjust my step vector v. That means I need to now take a call on how liberal or how harsh have I been while doing the n into ns function evaluations. So I will tell you a method to do it. Right now, don't worry about how do you adjust the step, but you adjust the step. And then you say, now we will reset ns equal to 0 again and go back. Now, this particular thing is called as the step adjustment. This you do nt times. So you do n function evaluations ns times, adjust your step and adjust steps nt times, and then again keep going back. So now when you come to this last yes, how many would you have done?
So nt into ns into n.
Exactly. N into ns into nt, right? Now you say, okay, I have adjusted my step nt times for ns cycles of n variables. Now you say, okay, now you say one iteration is over. Now let us reduce the temperature. That means let us multiply this original T by alpha T. And temperature will be lower than the previous one by a factor alpha. And whichever point is there in my memory so far as the best point, I keep it as the optimum point. I renumber I make again number of steps equal to 0. And then I again go back. Right? So when I come to this place, I have done n into ns into nt. Then it is one iteration. Now what I do is I keep on repeating this till I meet my stopping criteria. And let us say the stopping criteria is equal to number of function evaluations equal to, let us say 20,000. Now let's look at some numbers. Assume that we have a problem with 5 variables, so n equal to 5. Assume that ns is to be kept as equal to 10 and assume that nt is to be kept equal to 20. That means 20 into 10, 200 into 5, 1000. Right? After 1000 function evaluations, I am going to come here, n into ns into nt plus 1 I am forgetting. After 1000 functions I come here and then I say, have I reached my 20,000? No, no, no. Go back and repeat. Then again do this, do this, do this. You will come here, it will be 2000. Because second cycle, again you will do n into ns into nt. That is 5 into 10 into 20. So you will come here, 2000, no, go up. 3000, no, go up. Like that you keep on going. When you come to 20,000, you say test. And then you stop. So you can see that if n equal to 5 ns equal to 10, nt equal to 20, you will do 20 iterations because your criteria is 20,000 function evaluations. This is how the algorithm works. So now I'm going to take 1 minute to clarify any doubts, because now I am going to just give you a demo. Exactly 7:30. I have to give you a demo of this function and I want you to connive together and make it fail. So therefore, I would like your participation, but I would like to clarify any doubts that you may have at this point. Do you have any questions regarding the algorithm which I have just flashed and spoken to you? So I have to assume that you have understood everything. Unless you ask me questions, I can't go further. So as you have seen, this is very much function intensive. For a simple problem with 5 variables, I will get 20 iterations if I do 20,000. But actually I require around 200 iterations, which means I should make it 200,000. So if your function evaluation of x takes 1 minute, I will require 200,000 minutes. So this is a problem. Don't venture near this method if you cannot calculate your objective function fast. I used this particular algorithm as part of my PhD research, in which I had 20 variables, 10 constraints, one objective function, of course, which I had to minimize. And I remember I used to give 6 million function evaluations, and it used to take 8 hours of calculation. But it never failed. It always gave me results which I could depend on. Okay, so now I'll show you. There is a standard test function called as a Himmelblaus function. So how many of you know about this function? Have you heard about this function before? Because if you know, then I'll not waste time. I'll just quickly go ahead. So at least people can say yes and no.
No. So I mean, I have seen in lectures, but not I don't know about it.
Okay. So it's a very nice function. It's a sum of two squares, x1 square plus x2 minus 11 square plus this. So if I want to minimize the function, what would be the value? How will you get the value?
I can do a derivative and I can find out the extremum points, and then I can test which is which.
Then you are in the wrong class, sir, because we are not looking at classical methods. We are looking at, see.
So then.
Do you need to do that? Do you need to do that?
No, I mean, if we go by the simulated annealing method, then what I need to do is guess one point, and then
can we not solve it without essay and without calculus, using simple mathematical logic? You have a function which is a square plus b square.
Yes, of course.
It will be minimum only when a equal to 0 and b equal to 0.
Yes, of course.
Exactly.
Which means a simultaneous solution of these two equations. Value of x1 and x2, at which simultaneously x1 square plus x2 minus 11 is 0 and x1 square minus 7 is 0. No need to go to calculus, no need to go to essay. So one solution is 3, 2, because 3 square plus 2, 9 plus 2, 11 minus 11 is 0, and 3 plus 4, 7 minus 7 is equal to 0. But interestingly, there are 3 other solutions for this function. If you limit your domain to -6 to +6, if you limit your domain to -6 to +6, you will find that in all the 4 quadrants, you have one solution and the numerical value of the function is exactly equal to 0 at all these 4 points. So all of these 4 are global minima, local minima with equal priority. So if the solution that you get is any one of these 4, you should not be unhappy. Also, within this domain of -6 to +6, hidden somewhere here in between, there is a small bump here, is one local maximum at which f star is equal to 181.62 and the numerical value is x1 equal to -0.2708, x2 equal to -0.9230. This is a zoom of the function. And you can see that bump here in the center is where the local maxima is in a small domain, of course, in a smaller domain, correct? And the minima is at these 4 points. Now, if I want to modify this function, what I'll do is I will add a term like this. So now please tell me, if I do this, then what happens to the function? And what happened to those 4 solutions which I showed you? We had 4 local minima. If I modify the function like this, what happens to the function?
So the minima at 3 and 2 will remain where they are, but the other minimas will be raised up a little bit. And
Therefore, 3, 2 will become the global minimum and other 3 will become local minima. Correct? They will be slightly more than 3 than 0. Do you agree?
yes, yes.
And
Yes.
and the next thing is how much are they more than 3, 2, or the value of f which is 0 at 3, 2, how high it will go at the 3 points will be determined by the value of this factor. If I make this factor as 100 or 1000, then I will be amplifying the variation. So it will become very high value. But if I make the value factor as 0.0001, very small number, it will be non-zero addition, but a very small addition. So they will be very, very slightly local minima. Okay. So there will be one global minimum and there will be other will become the local minima. This I'm going to skip. We don't have time for this today. Now I'm going to run my algorithm. Now this algorithm was given to me by Professor Kalyanmay Dev of IIT Kanpur at that time. He has given it to me with no constraints as if I use it for a non-commercial purposes. So I'm very thankful to him for giving me this particular function. I'm just going to, I'm going to forgetting how to increase the, should be under view only, I think.
So you are looking for something, Professor?
No, I was just trying to increase the font so that is it visible to everybody?
It is visible to me, but if you want to increase the font, you could go to that menu.
Yeah, unfortunately,
So you
what
press
I'll do,
Alt.
I'll tell you.
You
I'll
press
tell you
Alt.
what I'll do. I'll just I'll just start again
Open it.
because I have hidden the menu and I forgot how to make it. So yeah, I want to show it. Yes. Yeah.
So if you
So
go
what
to
did you say?
Edit, Preferences, or
Yeah.
Editor Options.
Edit.
Editor options
Correct.
at the bottom.
It will be there.
And so you can have
Display. There you go. Thank you so much.
Apply.
Right. Now I think it will be more readable to everybody, right?
Yeah.
So what I have done here is I'm not sure if everybody knows Fortran here, but it's not important. What is important is that I have modified the subroutine. So it is f equal to x1 square plus this function plus a very small number factor times x1 minus 3 square plus 2 square. Remember, it's a very small value, but I'll just make it 0.1 to start with. And now I'm going to run it. It takes time to run for the first time. Okay, so now it asks me whether I have to give default values or input from file. I'll just say file because I've already made one file containing the input parameters. I'll just I'll just give a name as okay, RSP. That is my initials. It has run, and if I open the file RSP, this is what it is. So it says that there are two parameters which are to be minimized. So maximization is false. I have a very high initial temperature. It is actually 10 power 9. There is this RT, which is the temperature reduction parameter. That is, you multiply the temperature with 0.85 in each iteration. This EPS is a very small number. This is the minimum function improvement that I will accept in an EPS iteration. So in 3 iterations, if I don't get improvement better than 0.1 10 power minus 4, I will say enough, let us stop. NS is 20, NT is 5. Those parameters which I told you. And maximum evaluation I've given as 500,000 because for me it takes milliseconds to run. ISEED1 and ISEED2 are two random numbers which create the sequence of random number generation. And the starting value given was -2 and 1. Okay. Lower bound -6, upper bound 6. Upper bound 6. And let us see what do I get as the result. It has gone to 3,2. But the function value which should be 0 is 10 power minus 7. You will agree that it is almost as good as 0. But look at this. It required 39,801 function evaluations, of which 28894 were accepted and 10462 were rejected. And the temperature was 10 power plus 9 in the beginning, right? The temperature was 10 power 9 and it has reduced and it has come to 10 power minus 4. And IER equal to 0 is an indication for me that everything went as per plan and we can believe the solution. So this is what it is. It achieved termination criteria and therefore IER equal to 0. So as you can see, we began from a point minus, I think minus 1, 1, and we have come to the optimum of 3, 2. Now I would like you to tell me. So I'll also show you one more thing. I'll show you the input file also. I'll show you the input file. Yeah. So now I would request someone to please help me. I print one only the printing command. Now someone has to tell me what they would like to try. We tried from -2, -2, 1, it went to 3, 0. So tell me something, tell me what you want to try. Do you want to try some other trial point? And I'll make the changes and I would like you to see the effect of that. So anyone can volunteer.
So the trial points are these the seed.
This is the trial point. This is the
okay,
trial point. -2 and 1. Design variable initial value.
So let us do -6, -6.
Okay. So you want to start from the edge of the domain. Okay, no problem. We can do that. It is a feasible point because it is within the bounds. Now seed has to be changed randomly, just to ensure that we don't, we have to be skeptical. Okay, for a moment, I would suggest leave everything else the same. And was it Akshay who did this?
Yes, yes.
So Akshay, we will run the code with your name. So I will run the code. And we will say that we will use the files and it will be called as Akshay or Akshay 1 because you may give more than one.
Okay.
Okay. So Akshay 1 has been created. So the starting point is -6 to -6. Seed is 2, 2, 3, 4 and 4, 5, 4, 6. Now let us look at this. So when it started, the function value at -6 minus -6 is 904.5. Okay, this is where it started, 904.5. Now I will first go to the solution. Oh, we have got 3,2 as a solution. This time there are 39,401 evaluations, of which 2873 have been accepted and 10,000 have been rejected, and IR equal to 0. So we have got 3,2 again, Akshay, from -6 to -6. Okay. Now anybody else would like to try? Yes, tell me what change to make. So I am curious, I don't know what about you. What happens if you start from the optimum point? Suppose we start from 3,2.
Let's do 3.01, 2.01.
Okay.
Yep.
Near optimum. We'll give the name as near optimum. Something has gone wrong. It doesn't, it should not. So maybe there is a problem with the, so let me see what is the problem. Oops, I should open it from there only. Yeah, we began from 3.01 and 2.01. Okay. Okay, so the function value was very small, but you see the iteration number minus this is, there is some problem with the iteration number. But let us see what happened. Okay, it has gone to 3,2. So it has worked. We started almost near the optimum point, but we had to do 39,601 evaluations to come to a conclusion that the solution is not 3.01, 2.01, but 3,2. Function value is 10 power minus 7. Okay. So Akshay, it has worked, right?
Yeah, yeah.
Okay. Now let us see if you can, if somebody can make it not work. Yeah, please tell me. I am inclined to start it from 3,2 exactly. Just to confirm that the objective function value is exactly equal to 0 in the beginning. And then what will happen? So this is for my own curiosity. I will call it as optim.out. So I began from 3,2. The range is -6 to +6. Very good. The function value is also 0 in the beginning. Temperature is 10 power -9, 10 power +9. Minimum value so far is 0, which is in the first iteration only. And where do we go? We end up in 3,2 again. The function value is 0 and you have gone to 40,401 evaluations, out of which 21,000 of them were rejected. So it has worked, isn't it? Now this algorithm does not have any intelligence to realize that the current point where you started is actually the optimum. Don't go anywhere. That information comes only by calculating derivatives, but or the gradient, to be very precise. But gradient requires derivatives, and that may not exist. So in a function where we don't get derivatives, or where you don't want to calculate derivatives, you have gone through 40,000 function evaluations. But if I plot now for you the motion of the algorithm, I can show you that. If I plot for you, I can just open that and show you. There is a history file. Okay, it has not gone anything because it didn't find any new point better than the first one. So there is no history. But I will look at the logbook. There is a logbook file where I keep. Where is my logbook file? Yeah, this is my logbook file. So you can see first calculation was 3,2. The function value is 0. Then it went to first change, 3.138 and 2. The function value is slightly more than 0. Then it kept this one same. It changed the second one. It got 2.7. Then so this 2.7 is worse than 0.7, but accepted because you are in the beginning. So this point was taken, and then you changed to this to 2.5. This is same. It went on the whole thing. It went on. It became very bad, etc., etc. Finally, let us see what is happening in the end. In the end, he is oscillating near where? He is oscillating near 3,2 only. And finally, he converges at 3,2. So if I actually plot this, on by taking this line, you will find that it will start at 3,2, go all over the domain, and again come back to 3,2, which is what we want it to do. We don't mind it to go all over the domain, but we want it to ultimately end up in 3,2. Okay. So now, can someone please make it fail? Tell me what to do so that it fails.
You start from the upper bound points.
It will not work. We just now began from -6. It worked, no? Okay,
No,
I'll
sir.
try it for you. That is what you want or something else?
Yes, sir. Exactly, sir.
Okay. What's your name?
My name is G. Bhattacharya, sir.
Bhattacharya. Okay. 1 minute. So, what is your first name? D stands for what?
D stands for Dibyendu, sir.
Okay. So I'm going to put your name. So I start from the files. Is it correct?
Exactly, sir.
Let us see. Dibyendu. So we began from 6,6. The function value was 2188.5 to start with. And where do we end up? 3,2. Function value is 0.5, 10 power minus 8, 40,000, 29 and 10,000. Did you notice that the number of function evaluations are almost the same each time? 38,000, 40,000, in that range. So it worked. Okay, open challenge for anyone. Make it not work. One simple way would be to make temperature very small. So I'll make temperature as 0. No, I'll make it 10 power minus 2. Temperature is 10 power minus 2. Everything else is same. Earlier it worked, right? You got the answer as 3,2. Now let us see if I just make temperature very small, what happens? Low temp, I'll call it. Six comma 6. The same 2188.5. It has worked. So even if temperature was taken very low, because I have given large number of function evaluations, it has still worked. So if I really want to make it fail, I should even reduce the number of function evaluations by a small amount. See, it's difficult to make it fail. I'm just trying to show you. It's not easy to even make it fail. It works every time. Please fail. Hopefully it has failed. So it began from 6,2. Okay, same number 2188.5. My God, even with 5,000 evaluations, but I got IER equal to 1. Okay, so it says consider increasing max eval or EPS or decreasing NT or RT. These results are likely to be poor. Okay, but they are not poor actually. Actually, it is 3.0001, 2. So even with that also it is working. So as I mentioned to you, it is difficult to make it fail. But I am hellbound to make it fail. So now I will do the worst thing possible. And that is, I am going to make RT as negative. No, not negative. I'll make it as 2. So now what is happening is temperature is not going to decrease. It is going to increase with time. Now it should fail. I will just say positive RT. So we start from 6,6. And where do we go? See, even when then, even when I'm trying to crack it, it is still working. So temperature is 1,67,000. It is giving me a warning saying that the results are likely to be poor. But actually it has given me a solution because it found it randomly somewhere. In one of the function evaluations, it has found this solution and that is the best soup. This has come purely by hit and trial. Okay. But you can see that it's not very easy to make it fail. Let me try one last time. What can I do? I will make ns equal to 2. Let me see if that works. I somehow want it to fail. I'm sorry, I can't make it fail. It is so good that it is still able to get a reasonably good solution even though the warning is 1. Now I want to show you that if I actually give the correct values, it will give me good solution, better solution than that, because I have been messing with the input file. So let me go back to the what I think is the correct value. And let me also change this arbitrarily, just to make sure that there is no problem because of this one. Yeah. Now we are back to exactly 3,2, and I'm happy because I believe because IR equal to 0 means everything is done correctly. So now I can believe these results. So as you have seen, even when you choose the parameter slightly wrong for a function like this, it is able to come to the near optimal solution purely because it is searching the whole domain. Okay, so it is going to take me effort to fail. I want to do one more trial and then we will stop. If I want to make it fail, what I will do is I'm going to reduce this penalty to a very small value. That means now all the 4 points are going to be actually quite similar. No, this is called as low factor. Low factor. Even when I gave such a small penalty, it is still giving me this solution, but this can be taken care. This can be taken care by, yeah, this can be taken care. I'll just change the starting point to -6, one of the other corners, and I hope it goes to some other optimum solution now. -6, function value is 1490. Still 3,2. Actually, any of the 4 are acceptable, na? So this is not a wrong solution, but if I keep on arbitrarily changing the trial point, it can get one of the other three solutions also, and we should be happy about it. No, it's going to 3,2 only every time. But we can't complain. We can complain because this is also an optimum solution. IR equal to, nobody can say that this is the wrong answer. It's just that I'm not able to show you that it can go to any of those four. It should be able to go. If I keep on trying this, it will able to go. Okay, so I think we can stop here. This is a simple test function, so maybe we are not able to demonstrate the power, but I think you get the message that if it is used properly, you will definitely be able to get at or near the global optimum. Oh, I'm sorry. Suppose I make it, no, then in that case, it will definitely go to 3,2. Yeah, I mean, I have to just try it at various starting points. Okay, Akshay, I think we can stop here.
Okay.
Unless somebody wants me to try something, I would like to stop.
So participants, any more guesses? No?
Please make it fail. I'll be happy. I can sleep peacefully. It's not failing.
If we replace this plus by minus symbol, then
Okay.
the global minimum will change.
Yeah, but then you are changing the function itself, no? So you will get a solution. Okay, I get your point. You will not get 3,2. But you know what will happen? It may go negative. And if it goes negative, then it will crash because objective function cannot be negative in case of simulated annealing. Okay. So objective function has to be positive. I can try and let us see what happens. I have never done this before because that is a totally different function. But let's do it and let's see what happens. Negative factor is what we will run. So negative factor, it has gone to this number, minus 3.9 and minus 3.4447. Function value is minus 75. You can see. Now the thing is, this is the global optimum. Now you keep running many functions. I think it will go to the same point. So let us just check that. Okay. Just keep it in mind, minus 75.79 and minus 3.9, minus 3.4. Okay. If I just change the input file and I say that don't start from this point, start from 6,6. Everything else is same. So now my starting point is different. I'm just calling it second. Same point. So whatever function you created, wherever you start, it is going there only. So you have made some new function and it is able to find the optimum of that irrespective of where we start from. We can do one more trial. I will start from the optimum 3, 2. And it will go to minus 75. Three comma 2, function value is 0. There you go. Same point. So it began from 3, 2, but because the function is changed, it is finding that solution each time. And just to confirm this, I will just make it plus 1 times and now it will go to 3, 2. So start from 3, 2, function value is 0. 3, 2, function value is 0. So it works. Okay, I think on that note we can stop. It's too late also for you and for me also it's getting a bit late now. So I think we can stop here. Thank you so much for giving me this chance to share this with you. If there are any questions, we can take them. Otherwise, we can.
Sir, I have a query, sir. I have a query, sir, from electrical point of view. Sir,
Yeah.
what you said earlier that Metropolis Hastings criteria, that probability of P is equal to e to the power minus energy divided by KT. Sir, I got some similarity with this equation of a diode current. I0 by I is equal to e to the power minus QV by KT. Reverse saturation current and divided by I, that is equal to minus e to the power minus QV by KT. This looks more or less QV is the actually energy level of the electrons, and V is the voltage, Q is the charge of the electrons, and QV is the energy level of that electrons. And I got it more similar with this Metropolis Hastings criteria. Some I have
That's okay.
just.
Yeah. So see, I don't know exactly what it is because I don't work in electrical engineering, but basically they seem to have used a similar approach for some problem in electrical engineering, which is fine. I think which may be working. So no issue at all.
Okay, sir. Okay.
Yeah.
Okay,
Anybody
sir.
else would like to ask something or discuss something before we close? Akshay, over to you then. Let us close the session.
Okay, so thanks, Professor Pant, and thanks also for this. So this is your brainchild, the workshop series. So thanks for that also.
Oh, no, it's okay. Yeah.
So the participants should note that Professor Pant will again have a session tomorrow. This is a health and wellness session, handling anxiety due to uncertainty in daily life. So please join us again tomorrow with Professor Pant, and of course we'll have normal sessions starting from 9:30 a.m. in the morning. So good night, everyone. Rest, and then tomorrow again we'll have the final day.
Yeah, one small announcement I want to make is that in tomorrow's session, if you are not participative, it will be totally boring for you, because tomorrow we are trying to look at a live problem with everybody faces, including me. So please, tomorrow, please be more interactive than today. I understand today is an optimization problem, but tomorrow it will be a live problem. So I hope that, because I'm going to ask you questions tomorrow, and I will not go ahead till you till you answer some of them or attempt to share your views. Okay. So good night, everybody. See you tomorrow.
See you tomorrow. Good night, everyone. See you tomorrow. But we start tomorrow morning, right? 9:30. Okay. See you. Bye. Thank you, Professor Pant. Good night.
Thanks a lot. See you.